was x equals r cosine theta, so it's something cosine theta. Y equals something sine theta. And then a new one for us, z is equal to rho times the cosine of y. So where we left off in the practice problems is now we have spherical equations that your rho equals 2 times the sine of phi times the cosine of theta. This represents some sort of surface in 3D. So what we're doing for these are the same idea that we did for cylindrical. We're trying to make it look like one of these. The goal is to write everything with only x, y, and z. So just peeking at this, do we have any head start of what we think we want this to look like?
Since rho is equal to the square root of x squared plus y squared plus z squared, you can set it equal to that?
I have no objections to that. But then what would I do with the right hand side?
No, it's not. It's not the
Well, sine phi cosine theta kind of looks like this piece. But it's missing a row. And no worries, you can get a row there. You can just multiply both sides of the equation by row. And now I'm going to multiply the left-hand side by rho also, which gives me a rho squared. All right, now this is feeling pretty good. Because if rho was the square root of x squared plus y squared plus z squared, that means rho squared is x squared plus y squared plus z squared. And now, what is rho sine phi cosine theta?
X.
So I get a sphere. So we get x squared plus y squared plus z squared equals 2x. If you were to move that over, you could do some completing the square, and you could get the equation of a sphere. And looking back, now I've got rho equals 2 secant phi. Looking back, I've got nothing that references secant. But I remember some pre-calc knowledge. What's another way of writing secant?
1 over sine. Cosine. 1 over cosine.
1 over cosine.
1 over. It's like secant.
But nothing in my list has a divided by cosine.
Right.
So I'm just going to get it out of the denominator and multiply both sides by cosine phi. I'm going to change the order just so it pops out a little more. There it is. Rho cosine phi is z. So this is z equals 2.
Wow.
So I pointed out in the last one that this represents a sphere. Therefore, what does z equals 2 represent?
A plane.
It's a plane. This is the plane parallel to the xy plane with a z coordinate too. So if we're wondering, like, what do test questions look like? I could just ask, what does rho equals 5 secant phi look like? And the options would be sphere, line, half cone, things like that. We would have to do a quick substitution. You land on z equals 2, and you go, oh, that's a plane.
It's not top on the sphere because the radius is 2x.
So if you had subtracted 2x over, you could do some fancy algebra called completing a square, and you could get that to be the equation of the sphere. So if you have x squared plus y squared plus z squared equals, and then all these pieces are linear in x, you would get a sphere. Linear in x, y, and z, I should say. Okay. the other way, I'm not going to lie, it's not that exciting. Very rarely does going from cylindrical to spherical actually do something meaningful. Unless you have any of these, you know, x squared plus y squared plus z squared, arctangent y over x, or arctangent this business, you're not really going to get anything exciting. So we can just make substitutions for what x is and for what y is. X is rho sine phi cosine theta. I'm sorry, this is supposed to be one. Rho sine phi sine theta.
Right. Fine.
And then z is rho cosine phi.
Square root both sides.
Well, I've got things being added, but maybe let's factor out rho squared.
Okay.
Now, if I want to solve for rho squared, I get 4 over this business.
All that. Okay.
So again, I'm not going to lie, you're not going to get something clean, like it lands on something easy, like, oh, rho equals 2, or something like that. So when in doubt, if there is no clever substitution, you can just plug in what y is. You can just plug in what z is. And kind of just work until you get an answer choice. This very easily could have been a multiple choice answer.
So with that, you're just going to leave rho squared? You wouldn't take
Yeah,
the square root?
so I could solve for rho, but when I take the square root, I get plus or minus. In my opinion, that looks uglier. I think this is a cleaner way. If this was x squared, y squared, and z squared, I could maybe get something clever here. So since I can't, I'm just going to make substitutions. Everything's got a rho in it, so I'm going to divide everything by rho.
And both sides should be squared.
It was just so small you couldn't see it.
Yeah, right.
And now we could do the same idea. There's a rho in both, so I'll factor it out. one more line. And I can just solve for rho by dividing both sides by all of this modulus. But again, go in this direction. Don't be upset if you don't get anything, sexy with this. Question? These, on the other hand, we need to have these just like locked in. So it says convert each spherical equation to its equivalent rectangular form. This is, if you guys remember what I put on this side of the board last time, this is equivalent to have if you just have x equals 2, y equals 3. In spherical coordinates, if you have just rho equals 3, what does just rho equals 3 look like in spherical coordinates?
Just rho equals 3, so you're coming out 3. It's a
So no matter where you
circle
go,
with 3, radius of 3.
a what?
A circle with a radius. Well, I'm saying, not a circle. Oh, right, a cylinder or something like. No, I'm still.
It's a sphere.
A sphere.
No matter where you go, in any direct circle, rho is that distance. Yes. So rho is just the distance from the center going all the way out.
Mm-hmm.
So if you go all the way out, any distance, the center of 3, you're just building a sphere.
A sphere.
Now, see, this is
Sphere.
not focusing.
Yeah, it's trying. Yeah, it's right. It's focusing a lot.
All right. So we've got rho equals 3. So we know this is just a sphere, but I do want to be able to convert this to its rectangular form. So I go over to my substitutions page, my toolbox, and I see, okay, that's right. Rho is the square root of x squared plus y squared plus z squared. So if I just square both sides, I get something familiar.
No. Okay.
And boom, there's my sphere.
Yes, there it is.
So another, question I could ask is, given this surface in 3 dimensions, which one of these spherical equations could represent that? You would recognize, okay, exam 1 tells me that's a sphere. So in spherical coordinates, that means no matter where you go, rho is 3. So you would match it to rho equals 3. The next one is phi equals pi over 2. So coming back over here, I have phi equals the angle coming down from the positive z-axis. So I hinted last time that phi equals something could be a half cone. But let's think about this equation specifically. What is phi equals pi over 2? So no matter, so I'm just coming down to pi over 2 in any direction.
It's like a circle?
Or a half sphere?
A cylinder?
Or
Plane.
Plane.
If I just drop down pi over 2.
Oh, okay, so just rotating from.
I think
Okay.
it's like a rectangle.
Because my phi can be anything, my theta can be anything, so you're just building.
Z.
What do you mean when you say that it could be a half cone? What is
So,
a half cone?
Say this were pi over 6.
Okay, so it depends on what it.
If phi is pi over 6, then no matter where I go, that angle of pi over 6, I've got half a cone. Or are you asking why half cone versus cone?
Yeah.
Cone is, so technically,
Oh, cone is like a reflection.
this is a cone. We've been lying to our whole life and saying that that's a cone. That is a half cone.
Yeah, it's like a reflection.
Double side action cone.
So I need to be able to show that phi equals pi over 2 is a plane. Couple ways you could do this. You could grab your, well, this is going to be arctangent, square root x squared plus y squared over z equals pi over 2. Now I want to get everything in terms of x, y, and z, so I can just take the tangent of both sides. Now this is the critical step here. What is the tangent of pi over 2?
That's like x over y. It's like y over 0. So it's like undefined-ish.
So hang on. I landed on that the tangent of pi over 2 is undefined. That means that this thing is undefined. And if I had a fraction and got something undefined, what needed to have been true inside that fraction?
Your
That
denominator
you
has
divided by
0.
0, or the denominator equals 0. So it needs to be true that the denominator equals 0. Ah, holy shit, there it
So
is.
it said pi over 2 and 3 pi over 2.
We got it. Z
Right.
equals 0, which is a what? It's your plane. And if you think about it, that makes total sense. I came down at an angle of pi over 2. That is just the plane. Z equals 0. Now, this will only work if it's pi over 2. This says phi equals pi over 2. If you plug phi in as pi over 2 into this equation, what do you get?
That's 0.
Z equals 0.
Yeah.
That's the only one where that works, though, because you need what the rho is, but since 0 times anything is 0, that's the only one where you just get Z equals 0. All right. Theta equals pi over 4 from my reference sheet. Theta is arctangent square root. Theta arctangent y over x. Before I even keep writing, do you remember what theta equals pi over 4 represents?
Yeah, square root 2 over 2. Or 1
Sorry guys. What does theta equals pi over 4 represent as a surface
as a surface.
in spherical coordinates?
Oh.
So theta, it's saying you can go out an angle of pi over 4, but your rho could be anything, and your angle could be anything. You're just tracing out a plane. I will convince you with the equation. I can take the tangent of both sides. What is the tangent of pi over 4?
That's 1. Yeah.
1.
1.
So you land on y equals x, which is a plane.
Yeah. Oh, and you got how's that y minus, x minus y equals 0?
So if you wanted to write it in that standard form,
Mhm.
x, y, z equals 0.
Okay, and then that's still x equals y. Gotcha, I'm sorry. Makes sense.
I know it's kind of crazy, but today's kind of when the class starts. Everything kind of up to this point is just getting used to 3D. How do things work in 3D? But this is Calculus 3. So the class is going to be entirely from this point on about functions and calculus. So everything, again, is just getting us used to 3 dimensions. The better news is everything's going to feel really, really familiar. We're going to talk about functions, domain, next time derivatives. It's going to feel familiar again. We're just building on previous knowledge. So today's going to be all about functions of several variables.
We will see.
So everything is going to be talking about functions in 3D. So what that means is you have an input, you get an output, normal function stuff. Talking about things in R2, we said that we input x into a function, and it's going to output a y coordinate. Pretty basic, what we did in middle school. So we said that the y coordinate is going to equal whatever you get when you plug x into your function. And we said the domain of the function is going to be all of the inputs where the function is actually defined. So if you can plug a number in and you get something back, boom, that input is in the domain of the function. So now in 2D, we are now going to take an input of x and y. So what does that mean? Our input space of a function now is no longer a number, but is now a 2D coordinate. So if I can get another color. This shaded region represents the domain. So again, a 2D coordinate system is now the domain of a function. When you plug that x and y into the function, you're going to get a number which represents is equal. So we've been talking about these as far as surfaces and geometrically building things in 3D, but now this is strictly, you plug in an x and a y together, you get is equal. So now my output gives me a z, where my z coordinate is f of x comma y. So in our Algebra 1 classes, we always saw, f of x equals, from this moment on, all of our functions are going to look like f of x comma y. It's a function that takes on an x coordinate and a y coordinate. So a previous knowledge, so R2. I had a function, and when we kind of picked up, f of x is kind of the same thing as saying y. True, but this notation just kind of, really emphasizes that this is a function that takes on x coordinates. And this notation is saying when you plug -2 into this function, -2 squared is 4, plus 3 is 7. This means in your xy plane, you have the point, the coordinate, -2, 7. And you could read this as saying, when you plug in -2, you get 7 back. So if I have the function f of x comma y, so first of all, when you walk up to this, you should recognize that this is a 3D image. You plug in 2 things for an input, and you get an output. So 3 variables, 3 dimensions. If we want f of 0, 2, this is saying, what is the output of the function when x is 0 and y is 2? So we get 12 minus 2 is 10. Now, just conceptually, I know it's kind of like, okay, I get it. Conceptually, why it's just maybe a little different is, in the past, we've always plugged in a number, and you get a number back. Now you're not plugging in a number. I agree you are plugging in numbers, but you are plugging in a 2D coordinate. So your input space is now a coordinate, and it's going to output a number. So you tell me what to plug in for x and y, and I'm going to give you the height. So if we think about what a function has to be in 3D, it still has this idea of like a vertical line test. If you draw a line perpendicular to the xy plane, then you should only get one number back. So spheres are not functions in 3D. They are surfaces, they are shapes that you get, but it's not a function. If you plug in 0, 0 into a sphere, you're going to get 2 different points, not a function.
Are spheres the only things?
No, it's actually like a lot of things that we looked at. We looked at, ellipsoids, hyperboloids. It has to be like a sheet of paper or a blanket that floats in space.
That can't be closed because I must say there's 2 points.
Yep, it's never going to curve around. It'll kind of, gradually go up, gradually go down, but almost like a blanket.
Essentially, it has to be like a blanket or a plane.
Correct. So let's just pause for a second and just review domain from like a pre-calc class. So no 2 dimensions yet, just normal functions for pre-calc. So if I give you a function that inputs one variable, only x, we've got a couple different restrictions that we can have. If you have a square root, you just think through it for a second and be okay, you can't have a negative under a square root. Can't you have 0 under a square root? Yeah. So if you get the square root, it means that everything underneath the square root has to be greater than or equal to 0. So in our pre-calc classes, we had lots of different ways of writing the domain. You could just write it as an inequality. You could just write, oh, x has to be greater than or equal to 4. Any x value that you plug in greater than or equal to 4 will work. You get a number. We also had something called set builder notation. So this was our set builder notation. We maybe saw it once, the first time we ever did this, and we never saw it again. It's the most precise way of saying the domain, all of the values that you can plug in are all values of x, such that x is a real number. This is really saying x is an element of the real numbers, but x is a real number, and x is greater than or equal to 4. We're going to write the set builder notation for all of these. When we get to multivariable, writing inequalities is not going to be what we need. We're going to want to write it as the set builder notation. For ln of x, the thing that we need to remember is that you can't take the natural log of a negative number. It means that everything inside the natural log has to be strictly greater than 0. So I'm going to say all values of x, x is a real number, such that x is strictly greater than 2. What do we think for the last one? Yeah, I have no issues there. And if that's true, we can say all values of x such that x is a real number. There is one last one that I need to write here. What could go wrong if you have fractions?
Divided by 0.
The bottom can't be 0. So you say the denominator can't be 0, therefore x can't be 2.
Right.
So for this quote-unquote set builder notation, it's really that you can be kind of quote-unquote descriptive with your domain. That's going to be what helps us with Calc 3. So now, let's do the same exact thing with Calc 3 functions. So if I have the function f of x comma y equals 4 plus 6x over y minus 2x, then I'm just looking over at kind of my, pre-calc knowledge. If you have a fraction, it just means that the denominator can't be 0. And while that is true, y minus 2x can't be 0, let's go ahead and solve for y when we're doing the domain, just to kind of make sense of what's happening here. It's saying y can't be 2x. So my domain is, I've got all x comma y, all 2D coordinates, such that x and y are both real numbers, and y can't be 2x. So again, it's kind of helpful that you can just use like a description of what your domain can't be. But writing it in an interval notation, you're writing all the values of x as an interval, but being able to just describe it and say, oh, the y can't be 2x. It's just a lot cleaner. Let's think about what this actually looks like, though. This is saying y can't be 2x. But it can be, quite literally, anything else. So let me justify this.
Wow.
So this is my surface in R3. This is the function f of x comma y equals 4 plus 6x over y minus 2x. What I'm justifying to you is you can plug in anything except points along the line y minus 2x. And here's how you can see the domain. Go to your bird's eye view. And you can see the domain, again, is a set of 2D coordinates. The best way to see the domain is just pop down, look at the XY view. And notice, you can plug in anything. You will always get a Z coordinate everywhere except along the line y equals 2x. Anything along that line, plug it in, you're going to get 0 in the denominator, you get something in the Say it. Because as you approach the line, you still get an asymptotic behavior. Because you're dividing by a super small number, the overall number gets really large. A lot of those, ideas that exist in Calc 1 still hold true. Let's do another one. So I've got g of x comma y equals a whole bunch of business. Just like we did in Calc 1, we always say, okay, well, square roots cause issues for us, but these don't. You can just ignore them. There are no values of x and y that make this go wrong. So for square roots, I'm going to set whatever's in the square root greater than or equal to 0. I'm going to solve for y again. Again, just be super careful. If you divide by a negative, the direction of the inequality changes. My domain is going to be all values of x and y such that both of them are real numbers, and it just needs to be true that y is less than or equal to 3x. Yeah.
Is it and? Can you just use a comma, or do you want the and word?
Oh, honestly, I don't think it matters. This is where Dr. Hansen or someone else comes up behind me and they're like, actually. If I want y is less than or equal to 3x, I want the line y equals 3x and everything shaded below and including the line. It would be a dashed line if it did not include it. If I graph y equals 3x, you're only going to get things strictly below that line.
So then on the exam, if you ask us to like sketch this, would we have to take that little
Give them ideas.
or just like that?
No, so you're just sketching the input space that you can plug. Or maybe another thing I could do is give you the region and say something like, which one of these functions has this W? Or something like that.
So we just shaded their input region.
Correct. Yep. Give you guys a couple seconds head start, put your heads together, find the domain of that. remember for natural logs? Strictly greater than 0. Yep. Second. So you could have solved for y. Then you get an ugly plus or minus. But I recognize what is x squared plus y squared, we'll just say for right now, equals that. Say it, circle. It's a circle in R2 with radius 3. So if it's x squared plus y squared is greater than 3, what am I looking at?
Above 3.
We're in R2. This is saying all points outside of the circle, but not including it because it's strictly greater than. If it was or equal to, then I agree it would also include the circle. And I know we're dying to see what this looks like in Lisbon. This is the actual function in 3D. And if you want to see the input space and you want to look at your bird's eye view, boom. You have a circle with radius 3, and you're only going to get points defined outside of that circle. Now, one of the questions you could ask is, well, what if the inside is always positive? Like, what if this was x squared plus y squared, and that's never a negative number? Then just like we said in Calc 1, that's fine. You're just never going to get any issues. You just get something that's always defined. There's your blank. Now, let me take this plus 2 out. You will have issues with x squared plus y squared. Because if x and y are both 0, you actually would get issues there. Because then you still get, an issue at 0, 0. So this would be defined for all points except 0, 0. You get this kind of infinite piece that goes down. So what if I asked you to identify the shape of that surface?
Can we plug it into Desmos?
Could. Zing? I'm not saying no, but why?
Because it's not squared. There's no squares. There's only y and there's an x.
But there are no z's, is that okay?
Yeah, that's fine.
Well, there is a z right
Oh, the z equals all that.
Don't forget f of x comma y
Is it?
is z.
It kind of looks like a line, so that's why it's not.
If you ever see something that is only linear in x and y, then you get a plane. Kind of like in Calc 1, if you only saw x, by itself, something linear, then you get a line. I like that. Well, the default in Calc 3 is if everything is linear in both x and y, then you just get a plane. That's like your normal kind of default now. Another question is, well, what if there was x, y, and z? Won't happen. Because this is f of x comma y. This is only going to be in terms of x and y. For now. So identify the shape. We see the plane. Another thing I could ask you to do is find all the intercepts. So thinking back to Calc 1, how would I find like the y-intercept? If I want the y-intercept,
That's when z's, that's when x is 0.
that's when x is 0. So extending that idea to Calc 3, if you want the y-intercept, what am I going to do?
Let's set x and z to 0.
Yes. Set both x and z equal to 0. So I'm going to give you guys a couple seconds to find your x, y, and z intercepts. I have plus 2. I was going to say, just to make it interesting.
That's good. Gotcha.
Can you get multiple x and y intercepts? Yeah, absolutely. Can you get multiple z intercepts? No. And that's the same idea as Calc 1. In Calc 1, you can get multiple x intercepts, think problem. but you can't get multiple y-intercepts because therefore you are not a function. Same thing holds true in calculus. You would not be a function if you got multiple z-intercepts.
About to leave, it wouldn't stop. I'm sorry. No, don't you dare. Damn Amazon.
So you don't have to only have functions in your rectangular world. You can have f of r comma theta, which is now a function of two inputs, an r and a theta, and it will output a z coordinate. So it would give you a point in cylindrical world. You can have a function that you input a theta and a phi, and it outputs some rho. So now you've got a spherical function. So when we start to do our calculus, I will let you know for Unit 2, we're going to be hanging out almost always in rectangular form. But starting in Unit 3, we're going to start expanding towards doing calculus in different kinds of geometries. But I do want to show you at least one of them. So consider the cylindrical function. So this is a function of r and theta. It's going to output a z coordinate. And just to show you, we can do all the same ideas. Find the domain. I know that I can't take the square root of a negative number. That means everything inside the square root has to be greater than or equal to 0. Practicing writing our domain, it would still be any r comma theta such that r and theta are real numbers and r is greater than or equal to 16. And you might be going, well, hang on, but theta is not really like a comma theta is a coordinate in polar coordinates. I agree it's not a distance, but it still describes a point in R2. So we would be responsible for recalling what does R is greater than or equal to 16 look like in now polar coordinates. R is the distance from the pole. So it's a circle. So R equals a number. So R equals 16 is a circle. But I want all points outside and including a circle with radius 16. Second? Yeah, R equals number, circle. Let me pass out some practice problems. I do want to leave you with the hard copy, so let me just get the copies of these problems, but I will put them on the projector so you have a chance to look at them before I get the paper. over these practice problems before we head out? A couple of them on the beginning are just making sure that we understand. If you want to evaluate a function, f of 1, 2, and we plug it in, get the number. 4 is going to be kind of we're just pulling from pre-calc knowledge of finding the domain. You're always going to get something in R2. You're going to get everything below a line, everything inside a circle, everything outside a circle. But it's always going to be a sketch in R2. 5 and 6 is just, okay, well, let's just extend this to a word problem. Nothing has to always just be strictly geometry. Oh, you live in a 3D coordinate system. You could have a function, t comma c, where now instead of just inputting, I don't know, the amount of time that goes by, you input 2 different things. You're still just evaluating it, but making sense of things in no problems. And the last 2 of just, making sure that this doesn't have to be a rectangular function, but I could give you f of r comma a, g of r comma a. All right, so when we come in next time, like I said, I have a feeling from now on you guys are going to feel comfortable again. We're going to talk about derivatives. We're going to talk about finding local max and local min. It'll feel very familiar. If we have any questions regarding Calc 1, let me know and we'll get you caught up. Bye, everyone. I'll see you Wednesday.
All right. I'm just taking pictures. I'm going to do a swap. Not take pictures, damn you. Okay. That's it. That's all right.